we're halfway through the semester, and so we're almost. I mean, it's been a wild ride, right? Buckle up, it's been a wild ride. Not that wild, but anyway, we're gonna keep on trucking through. We're almost to my favorite part of the class, which is chemistry. We have like a couple more lectures left before we get to chemistry, but we're almost there. Okay, so today we're going to talk about electricity and magnetism, which we had a little preview of that already last week during lab because we did the battery lab. I found out that if you put four batteries in parallel, you can blow up the light bulb. That was pretty fun. Um, Actually, I think I went up to five with some light bulbs, so maybe some of them were defective. And I saw that some of you did the same thing too, added extra batteries in series in your circuits to see what would happen. Um, so that was our kind of like our little primer or introduction to electricity and magnetism. So, in regards to electricity and magnetism, we have this thing called electric charge and electric force. Okay. So, electric charge is the fundamental quantity, right? We don't really know what it is. We don't know what charge is. We always tell you, like, you have a positive charge and you have a negative charge and you have a neutral charge, but in reality, we really don't know what charge is, right? But electric charge, we can describe it, right? We can use it, we can control it, but we really don't know what it is. So electricity, of course, runs motors, lights, heaters, ACs, stereos, TVs, and computers. Electric forces, on the other hand, though, they are at the microscopic level. They hold atoms and molecules together, right? Electric forces hold atoms and molecules together. Okay. Gravitational forces hold the universe together. Holds our planets in alignment with our in a circular, no, elliptical orbit around the sun, that kind of thing, right? And then magnetism is also greatly associated with electricity. Greatly associated with electricity. So, I guess the point of the slide here is just for you to know that electric charge is the fundamental quantity. Electric forces hold molecules and atoms together, and then um, gravitational forces hold the universe together. Okay. Good stuff. Good stuff. So your first question for today is this: which of the following does electricity not operate? Motors, lights, heaters, and a manual butter churner. And I picked a manual butter churner for that one there because of a recent episode of Hell's Kitchen I watched where they had to churn butter as a what was it, a punishment for losing a challenge. So I hear it's quite a workout to churn butter. Has anyone churned butter here before? Like manually? No? I thought of all of us, somebody would have that experience. I was hoping, anyway. I feel like the QR codes are working better for you, Carly. That's good. Ah, I didn't know that. Interesting. Okay, okay. Let's see how people answered that one. I always think a question is super easy, but then you guys surprise me sometimes. Just kidding. Just kidding. I'm not being mean, I promise. I promise. Okay, oh wow, that was fast. Oh, I forgot to change the option to A, B, C, and D. All right, 21 responses, and wow, okay. This is supposed to be super easy. Which of the following does electricity not operate? I'll blame myself since I forgot to put A, B, C, and D there. It just says option one, two, three, and four. But obviously, the one that's not running by electricity is the manual butter churner. I think the word manual gives that away, right? Since since electricity is not running that, but somehow we still had some people say some people did say that motors weren't running by electricity, and then lights, but that's okay. Maybe it's because I put option one, two, three, and four right there, huh? No, no. Like I said, I'll blame myself since I didn't put A, B, C, and D there for you. I forgot to change the options, the choices. Okay, so electric charge, electric force, of course. Let's talk about them specifically. Experimental evidence leads us to conclude that there are two types of chargers. We have a positive charge and we have a negative charge, right? In electricity, which is funny. Again, we don't really know what electric charges are, but we can describe them as being positive or negative, right? All matter is composed of atoms, which are composed of subatomic particles, right? And so inside the nucleus of an atom, we have the proton, which is a positive charge, and a neutron, which is a neutral charge. And then we have the electron spinning around outside the atom, and that's called an electron, right? And that's the negative charge. Okay. Glenn, we have an exam on Wednesday. Do you need me to bring you a laptop again?
Yes, please.
Oh, see, didn't I say? I called it. Called it. But yeah, so just remember, electrons are negative charges, right? They spin around the outside of an atom. The center of an atom is called the nucleus. It contains a proton, which is a plus charge, positive charge, and it also has neutrons inside too. You can identify an atom based on how many protons it has, but we'll get into that later. So note that the proton and the neutron have about 2,000 times more mass than an electron, right? So they're pretty heavy. So notice right here. See a proton right there, a neutron right there, right? Almost the exact same mass, right? Only off by a couple there, right? But they're still at negative 27, right? Which is really light. That's super, 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 super duper light, right? That's 0.1. That's 1.6, except that it's a 1 and 6 with like 27 zeros in front of it. So it's a really small number, but that's still heavier than the mass of an electron, which is at negative 31 exponent, right? So most of the mass of an atom comes from what? The protons and the neutrons, right? The electrons really don't make up much of that mass because it's tiny, tiny, tiny mass, right? And then, of course, we have our charges here. We know that one electron's charge is negative 1.6 times 10 to the 19th. And then a proton's charge is the exact opposite, right? Positive. And then a neutron's charge is 0, of course, okay? If an atom has the same number of protons and electrons, it's electrically neutral, which makes sense, right? Because it balances out, right? You get 0 charge if you have the same number of positives as you have as negatives, okay? Okay. So the next question is, which of the following is not a subatomic particle? I see I forgot to put the A, B, C, D, E again. Sorry. A, proton. B, neutron. C, electron. Or D, all these are subatomic particles. Let's see. Almost there. 18, 21. I think we have 22 people in here right now. There we go. 22. Well, actually, Glenn, you just showed up, so it should be 23. Yes, 23 people. Yes, yes. Wonderful, wonderful. Very good, very good. Only one person got this one wrong. The answer is definitely D. All of these are subatomic particles. The proton is positively charged. It's inside the nucleus of the atom. The neutron is neutrally charged, charge of 0, inside of the nucleus as well. And then electrons are outside and they're negatively charged. Okay. So there's this unit called the Coulomb, and that's the unit of electrical charge, right? That's called the Coulomb, named after a guy in France in 1736 to 18. Oh, I'm sorry, that's his life. Meant sometime during his life, during that year, those years, Charles Coulomb noted that a single electron or a proton is plus or minus 1.6 times 10 to the 19th coulombs, which is super small. It's very small charge, right? Very small charge. So we usually use the letter Q right here to denote charge, right? So you have excess positive charges, it's plus Q. If you have excess negative charges, it's minus Q. We have like a whole alphabet for you guys to memorize, don't we? So that mean different things. And the crazy thing is that some of them are the same letter, just capitalized in lowercase, and they mean two different things, right? So electric force, and electric force exists between any two charged particles, either attractive or repulsive, right? So that's pretty important. There's a reason why there's only one line on that slide, right? There's a reason why there's only one line on that slide. And that slide says this, right? If there's electric forces, there are electric forces between two particles that either attract each other or they repulse each other. Like my girlfriend who thinks I'm super repulsive right now, but that's okay. We're getting through it. You know, it just takes time. It just takes time. At least she's staying. At least she's staying at home now. She's not staying with her mom, so she doesn't want to throw me off a roof anymore. Okay, so we have this law, more laws, right? The law of charges, and it's a super simple law. Okay, like charges repel, and unlike charges attract, right? What does that mean? That means that if you have two positives together, they'll repel each other. If you have two negatives together, they'll repel each other. But if you have a positive and negative, they'll attract each other, right? So super simple there. Super simple there. The forces between two charged bodies is a direct proportion to the product of the two charges, and inversely proportional to the square of the distance of their distance they are apart, which is an equation I'll show you in a second. So don't worry too much about that definition. I'll just show you that equation in a second. But I wrote this there because this definition here is what Coulomb's law is. Okay? It's what Coulomb's law is. So here's Coulomb's law, right? Right here. The force equals a constant times the charge of the first particle times the charge of the second particle, right? Divided by the distance between the two particles, the charges of the particles, right? Squared. I always forget the squared. So if you want to make that an equation that's just like with letters and stuff like that, like a normal equation, force equals k q1 q2 divided by the radius, or the distance between the charges squared. And then also the k here, this constant here, is this Coulomb's constant right here, which is 9.0 times 9 to the, times 10 to the 9, what is it called? Newton meters per Coulomb. Newton meters per Coulomb squared. Don't worry, you won't have to do any math with this, but I want to show you a relationship in this equation. Okay, so an object with an excess amount of electrons is said to be negatively charged. That makes sense. An object with a deficiency in electrons is said to be positively charged, which makes sense, right? Because if you have less electrons than protons, then you'll be positively charged. Static electricity is a study of charges at rest, right? A study of charges at rest. Okay. I guess we'll get back to Coulomb's law in a second. So charging by friction is a transfer of charge by rubbing, which is going to happen a lot soon because it's starting to get cooler. So we're all wearing hoodies now and jackets, right? So charging by friction is a transfer of charge by rubbing. Okay. So here we go with some rubbing charges, right? If I have two negative charges, they repel, right? So here's there are two rubber rods here, right? And if one's negative and the other one's negative too, right? They'll repel each other, okay? But if I have two positive charges, they also repel, right? Two glass rods, one's positive, the other side's positive there, they'll repel each other, I don't know why they say repulse. It really should be repel. Same thing, I guess, right? But if I have one negative, which is the rubber, and I have one positive, they attract each other, right? The rubber rod likes to, uh, 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 sorry, the rubber rod is attracted to the glass rod. I was trying to come up with some kind of dirty analogy for that, but it didn't work out. It did not work out. So your next question is this: Which of the following is a law of charges? Two positives attract each other. Two negatives repel each other. Positive and negative repel each other, or all these are law of charges. Law of charges. There we are. I've got 17 people who have already done it. Good job. Oh, okay, 22 people have done it. Good job. Again, the vast majority, only 2 people got this one wrong this time, right? The only one that is true here is the two negatives repel each other. Two positives definitely do not attract. A positive and a negative definitely do not repel each other. So the answer here would be B. Good job. Good job. Good job. So before we had charging by rubbing, right? Well, I was talking about that, which is with friction. Now we have charging by induction. Okay, charging by induction. I honestly don't know why we have these slides right here, because the next slide will be about Coulomb's law, which we were just talking about Coulomb's law like 5 slides ago. Why didn't they just put it together? No idea. You can blame your book for that. But anyway, all right. Charging by induction is based on this. When you have a molecule, right? If the molecule's charges are within the middle, right, and they balance each other out, we call that a nonpolar molecule, right? We call that a nonpolar molecule. But if some outside force affects it, right, and it makes it so that those charges are spread out now so that one side has a positive and one side has a negative, we call that an induced polar molecule, right? We call that an induced polar molecule, all right? So an example of this happening right here is if you have a comb, right? If you have a comb, and say you like used it in your hair a lot. I don't know who still uses combs in their hair, but say you used a comb in your hair and you used it a lot, and you built up all the static electricity in your hair. Well, not in your hair, but in your comb, right? And then you brought it towards some little pieces of paper, right, that were normally not charged, and then suddenly the comb attracts the paper, right, and makes the paper move. That's called an induced charge. And the reason why is because before the paper's charge was like in the center, right, where it balanced out. But then when you used the comb in your hair and made all this static electricity, it turned the comb negatively charged. And it's so this is the outside force, right? This is the outside force that makes it induce a charge by moving the positives to the left-hand side and all the negatives to the right-hand side. And so now there's a strong attractive force because opposites attract, right? Opposites attract. Everybody understand that? Understand what an induced charge is, right? It's um, and let me ask you this question: when you have static electricity, is it always there, or is it like go away after a while? It goes away after a while, right? You know, the static electricity is not always there. So this kind of induced charge is temporary, right? An induced charge is very temporary. Okay. So back to Coulomb's law. I don't know why we skipped, all the way over here to talk about Coulomb's law, but Coulomb's law again says that the force of attraction and repulsion between two charged bodies is directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. All of that is just to say, right, is that this. So remember, this is the force, right? F is force of attraction or repulsion, and then the constant here, and then these are the two charges here, and this is the radius. I mean, not the radius, the distance here, right? So the distance, as it gets bigger, the force goes down, right? But then as the force goes down, the distance goes up, or as the uh, charges go up, the force goes up, right? So the force of attraction between two charged bodies is directly proportional to the product of the two charges, right? So the force here, as if it goes up, it's proportional to the two charges going up, right? But it's backwards when you're talking about the force with the distance squared, right? The further it gets apart, right, the less the force there is. The bigger the distance, the less the force. The closer the distance, the more the force, right? So just remember that if F goes up, Q goes up, but R goes down, right? But if F goes down, R is going up, Q is also going down, okay? And you can see that by just seeing that it's inside the denominator. If you ever have a variable that's in the denominator, it will always be inversely proportional to the thing on the other side of the equation, right? And again, I won't ask you to do any math with this, right? But I might ask you if you put more distance between two particles, what will happen to the force? Does that make sense? Okay. So the thing I want you to notice about this Coulomb's law is that it looks eerily familiar to Newton's law of universal gravitation, right? I mean, there's the force, and there's the force. There's the distance, and there's the distance, right? Here's Coulomb's constant right here, which is K, but here's Newton's gravitational constant, G, right? And here in the gravitational, universal law of gravitational constant, here in the Newton's law of universal gravitation, it's the mass times the mass, right, of the two objects. But here, it's the charge times the charge, right? So they're it's almost exactly the same, right? Both of these depend on the distance of between the two things, right? Both of these, the law of gravitation and Coulomb's law, right? Both of them depend on the distance between the two objects, right? The distance between the two masses or the distance between the two charges, okay? Coulomb's law can describe whether an attractive force or repulsive force, uh, Coulomb's law describe either an attractive force or repulsive force. Gravity is always positive. So that's one thing to note though, right? Coulomb's law can be negative or positive, right? Because it can be attractive or it can be repulsive, but gravity is always positive. Because like if gravity were negative, I guess you'd be going through the ground, you know? You'd be like, in the dirt. It's probably where my girlfriend wants me to be right now. That's okay. I'm over it. I'm totally over it. I'm over it. I mean, if we weren't getting better, why would she be back in the house, right? Right? I mean, like she'd still be with her mom. I mean, it could be the fact that her mom's house is getting renovated right now and she doesn't want to be there with all the noise. But I like to think it's because we're getting better, right? I think that's what it is. Electrical charges are much stronger than gravitational forces. Electrical charges are much stronger than gravitational forces. All right. All right. So here's your next question. The equation of what law looks very similar to Coulomb's law equation? Newton's second law, Newton's law of universal gravitation, the third law of thermodynamics, or none of these laws? And of course, you can assume it's A, B, C, and D, of course, because I keep on forgetting to do that. Caitlin, is it your phone that's having issues now?
I guess.
I try to make it clearer too, so that people can see it better. But it's I think it's the resolution of the screen. I'm gonna request a better monitor, better projector. That's what I'm gonna do. Coulomb's law equation, 13 responses so far. Ooh, 20. Wow, you guys are fast. 21 responses already. Oh my God. I'm so proud. I'm so happy. Yes. Oh my God. Dang it. Dang it. You guys did that on purpose, didn't you? Just added one in there that was wrong just to make me sad. As if I'm not already sad. The answer here is Newton's law of universal gravitation, right? Definitely not D. None of these laws. Okay. All right. So let's take a look at the electric field now, right? Action at a distance concept replaced by the electric field, which surrounds the charge and present in the effect of the nearby space. I have no idea what that statement means. I feel like it's missing some words, right? But here we have electric field. So here we got a proton, right? And it's emanating, right? It's emanating some field, right? An electric field. And so here we can see how a proton, or not a proton, but a positively charged particle here, it's still emanating the field like we see here, right? But here's a negative charge, right? Here's a negative charge, and we can see how the negative charge's field kind of complements the field of the positive charge, right? It complements it, and that's why they attract each other. And the reason why it's a complementing it is because if you notice on the positive charge, right, the field is going away from the particle. And so here we see the field going away from the particle. But in the negative charge, the field is going within the particle, right? It's going into the particle. So it's like the positive charge is giving away electric field, and the electron or the negative charge is happy to accept, right? It's totally a give-take relationship between these two right now. Okay, give-take relationship. And sometimes, a relationship has to be that way for it to work out, you know? So I'm sure that couple is very happy. But when you have two positives together, right, they're both, exuding energy, exuding electric field, all going out of the particle, right? And that's why they repel each other. That's why they repel each other. So everything I just said there is this stuff. I have no idea what that means. Like, I don't know who wrote that. That's a very confusing sentence to me. Okay. All right. So let's talk about phrases. No, electric. No, terms. Terms. We'll talk about some terms now that have to do with electricity, right? So we have I here, right? I means the electric current, right? How much current is going a into a into a system, right? Into a system. Okay. So a good example of current and how current is so important in your lives, right? Is have you ever had this problem where you had a charging block, right? Like a wall charging block that has a USB thing in it, okay? And you'll plug in one of them, right? And you'll plug in one of them into the wall with a USB thing, and you try to charge your phone. It takes like 3 or 4 hours, maybe 6 hours to charge your phone. But your friend has another one, and it's black, right? And it may be at 2.5 amps instead of the 1 amp of yours, right? And then when you use their charger, your phone charges in like an hour completely, right? So that's what amperage is, right? It's how much current is coming into whatever you're putting it into, right? And if you're talking about your phone, if you got a 2.5 amp charger for your iPhone, right? Which is really nice because then your thing will charge super fast, right? A whole phone will charge in like an hour or two, right? But you have to buy that separately because it costs more, right? The phone charger that comes with your phone, it's like a 1 amp charger, okay? So the higher the amps, the more electrical current is going through, and the faster your phone will charge, okay? This also happens too when you try to use like uh, aftermarket charging blocks for like your Roku or your Amazon Fire Stick. You try to plug it into your Amazon Fire Stick, and the Fire Stick just won't turn on. You're like, what the heck's happening here? I have it plugged into the wall. It's not turning on. Well, it's because that little block, the little wall block thing, adapter thing you have for the USB, isn't high enough amperage, right? So funny thing is that most Roku's and Amazon Fire Sticks, Google, what's Google's called? That circle thing. I don't know what it's called. Maybe it's probably because it's dead is why I don't know what it's called anymore. But anyway, they all require at least a 5 amp charger or a 5 amp block, right? And that's why a regular iPhone USB wall adapter won't work to turn on your Roku or your Amazon Fire Stick, right? So current equals the charge divided by the time, right? Current equals the charge divided by the time. And of course, Q is charge, electric charge, right, in coulombs. And then time is the time for the charge to pass to pass a point, right, usually in seconds, okay? So 1 amp or 1 ampere, which A is the unit, right, equals the flow of 1 coulomb per second, right? So if you had that super cool iPhone charger that goes at 2.5 amperes, right, then it's going 2.5 coulombs per second, right? Does that make sense? Yeah, yeah. I'm telling you this now. You're gonna go to Walmart tonight and look for another charger for your phone that has at least 5 amps just to charge your phone faster. I'm telling you, that's gonna be a great time for you. Okay, great time. All right, so you can rearrange the equation where you have Q on this side, the charge on this side, and you can have the current and the time on the right side, right? So now 1 coulomb equals 1 amp per second, right? 1 amp times 1 second, rather, right? Therefore, 1 coulomb is the amount of charge that flows past a given point in 1 second when the current is 1 ampere, okay? So, have you ever heard of amp hours before? Like milliamp hours? If you have those charging blocks that you can buy, right? If you don't want to charge your phone plugging it in, you can buy like a backup battery kind of charging block, and you plug in your USB in there, right? And it'll charge your phone for you, like, wirelessly, portably, a portable battery pack. Those are all measured in what they call milliamp hours, right? Which is this thing right here. Okay. So most people buy cheap ones, and they're only like 2.5 amps or 2,500 milliamp hours, and you'll maybe charge an iPhone halfway with that, right? But if you get one that has like 10,000 milliamp hours or even 20,000 milliamp hours, I'll guarantee that's going to be more expensive, right? But if you get something that's like 20,000 milliamp hours, it'll charge your iPhone, your iPad, and your MacBook. It's great times, right? Spend the extra money. Get one that has more milliamp hours, okay? Get one that has more milliamp hours, okay? All right. So now let's talk about electrical conductors and insulators. Okay, electroconductors and insulators. An electroconductor is a material in which an electric current flows readily, like most metals, right? Due to the outer loosely bound electrons, right? Loosely bound electrons. I didn't tell you this before because we haven't gotten to the chemistry section yet, but when you have a metal, especially metal alloys and metal bonds, electrons are kind of like in this, what they call the electron sea, and they just kind of float back and forth like this. They just float, the electrons do, right? They're just, you know, like this for a long time, right? And there's floating, right? And so when you apply electric current to that, it's so easy for those electrons just to flow off because they're just floating, right? They're very loosely held together by those metals, right? But other things though, like wood, right? Or things that are like water that doesn't have any ions in it, or rubber, they're not metal bonds. They're like covalent bonds, and the electrons of a covalent bond are stuck inside of a bond, and so that's why they don't transfer electricity as well, and that's why metals do, right? So speaking of not transferring electricity as well, we call that an electrical insulator, right? An electrical insulator is materials that do not conduct electricity very well due to the tight electron bonding. Oh, I just said that. That's crazy, right? It's almost like I know what I'm talking about here. Wood, plastic, and glass, right? So the thing I want you to get from this is that in metals, Electrons are floating on this thing called the electron sea on the outer surface of the metal, right? And so those electrons are super easy to remove, make them flow to other places, and that's the flow of electrons is electricity. But in other things though, like wood or plastic or glass, those electrons are stuck inside of bonds, right? And they can't move as well, and that's why these things are electrical insulators. Then we have the semiconductor, which is not as good a conductor or an insulator. So one of those, an example of that would be graphite. And you see semiconductors most commonly in microchips, right? Like the i7 or the Mac M1 microchip or the i5 or the Xenon chip. Those are all CPUs for a computer. You don't need to know that. I was just giving you an example. Like, haven't you ever opened up your computer and you saw that little sticker inside your computer that says like Intel inside i7, right? Or Intel inside i5 or i3? Those are all microchips, right? And they're all made of semiconductor material. See, I mean, chemistry is all around you. Science is all around you. It's crazy, right? It's crazy. Funny story. They used to make semiconductors, or not semiconductors. They still do sometimes. They make like microchips and processors, central processing units for computers out of gold. And so people would go to like junkyards and find like old computers, like super old ass computers. Excuse me, I didn't mean to say that. Old computers, really old computers at junkyards, right? Just to get their chips out of them, and then they would melt down the parts, right, just to extract the gold from it. It's crazy stuff, man. Crazy stuff. They don't get the semiconductor out. They don't care about that. They just care about the gold inside, right? They just care about the gold inside. And let me just tell you, there's not that much gold in there either. So you got to get like a few tons of old computers to get like a gram of gold. So, well, a gram of gold these days is like $2,000 or something like that. So, so don't invest in the stock market. Invest in gold, right? See, look at that. You come here for science like tips, but I give you financial advice too, right? Don't hold me to that though, okay? Because I'm not a licensed financial advisor. Which I actually just recently found out that you don't have to be licensed to be a financial advisor. You could just be just Joe Schmo and be a financial advisor. Hi, I'm a financial advisor. Invest in my 401k, right? Yeah, you'd think that these people that you give your entire life savings to would have to be licensed. Nope, they don't. Makes me scared. Okay, which of the following does not act as a good conductor or insulator? A, an electroconductor. B, electrical insulator, or C, a semiconductor, not semicolon, a semiconductor, or all of these are terrible at both. Maybe we should be investing in Dogecoin or something, like Bitcoin. You guys know Dogecoin, right? It's like that Bitcoin that has that picture of that dog. It was made up like a few years ago as like a fake like Bitcoin thing, and then everybody like loved the Dogecoin so much. Now it's like the most valuable Bitcoin there is, just because it has a cute dog on it, which I don't think is very cute. I think my dog's cuter, but whatever. I specifically don't invest in Dogecoin because the dog looks ugly to me. Okay, so once again, good job. The vast majority of you got that one correct. The answer here is the semiconductor, right? Is the one that doesn't do either very well. And the other thing you can use to actually answer this question is the fact that semi means half in Greek, by the way, and then conductor. So this is like half as good as a conductor, half as good as a conductor. All right, okay. So this is just an example problem. I'm not going to give you any math, but I just wanted to go through, how we use certain things. Okay. So if I have a wire and it carries a current of zero point 0.5 amps, man, that's very weak, for 2 minutes, right? First thing is how much charge goes past a point in the wire in this time. And then second one is how many electrons make up the amount of charge, right? So you're given here the amperage, right? Then you're also given the time here is 2 minutes, which we always convert it to seconds. Every calculation we ever do is always in seconds. So 120 seconds, right? And what we need to get is the charge and the number of electrons. Okay? So the first thing we do here is we do the charge equals IT, right? And not information and technology, but amperages and amperage and time, right? So zero point 0.5 times 120 equals 60 coulombs, right? 60 coulombs for the amount of charge that goes through, okay? And then to solve for B, right? We just take the number of neutrons, the number of new electrons here equals the number of coulombs divided by the charge of an electron, right? That was the charge of an electron. And that's how you get the 3.8 times 10 to the 20 electrons, right? So I'm not going to make you do any kind of calculation like this, but I want you to know, right? If I show you an equation like this, Q equals IT, what can you figure out from that? You can figure out the amount of current. It's not the amount of current, the amount of coulombs charge going through the wire, right? And you can also figure out the number of electrons coming through the wire, right? So what you could do is you could go home and stick like a multimeter into your plug, your outlet, see what the amperage is, right? And calculate how many electrons are coming from your wires in your house. Just be super careful. You don't want to electrocute yourself. Okay? Super careful. You ever, as a kid, stick a fork into an electrical outlet? I've done that. That's not a good idea. It's a very bad idea to stick a fork into an electrical outlet. It hurts. Well, not even it doesn't even really hurt. It's more like it shakes a lot. Anyway, okay, so we also have this thing called electric potential energy, or sorry, I guess I'm dyslexic. Electric potential energy, not potential electric energy, but potential electric potential energy, right? So, God, I keep on saying it wrong. Whatever. We have that electric potential energy, right? And here we have some unseparated charges, right? And so there's really nothing going on there, right? So we need to do some work to separate these charges, right? But once you have the charges separated, right, you've got potential energy now because they're attracted to each other. Does that make sense, right? Right here, when they're close to each other, right, there's not much potential energy going on because there's not much movement for them to come together to do work, right? But on over here, if we separate the charges out like this, right, now they're going to be drawn to their opposite, and when they get drawn to their opposite, right, you can actually do some work, right? And so the quintessential example of this is called gel electrophoresis, right, where we use electric current to actually separate things like proteins and DNA when we do genetic profiling in forensics, right? When we do genetic profiling in forensics, right? Um, so DNA is actually pretty negative, right? And so if you take, a suspect's DNA and you chop it up into a whole bunch of pieces, right? And then you put it into a gel and put on one side of the gel a negative charge and on the other side of the gel a positive charge and turn on the electricity, the DNA will go into the gel and go towards the positive charge because negative DNA is attracted to positive DNA, right? And as it does that, it separates the pieces of DNA out, and that's what we call a genetic profile, right? Or a forensic profile. And that's how we are able to find suspects who have murdered people sometimes, right? It's good stuff. If you want to know more about that, take my forensics class in the spring. And sign up now because it's already filling up, even though registration hasn't opened yet. So it's not filling up at all. But still, sign up for it anyway. My forensics class is going to be a good time. If you want to hear about my cases I solved when I was working, half of it will be me talking about cases I solved and showing you pictures and talking about it. Because before I came here, I solved 100 cases before I left. and a lot of them were super fun. So, not fun while it was happening, but interesting is what I meant. Okay, so, and we did some electrophoresis in there too, so you get to see that. It's a great time. You see how electricity does work, right? All right, so voltage. Here's another term involved in electricity, right? Has anyone ever heard the words, the phrase, the voltage is what kills you, right? So the higher the voltage is it's what kills you when you touch it, right? So maybe the 120 volts in a wall plug, you know, is like on the fence. It's not enough to kill everybody, but can't kill little people maybe. Because when I stuck my fork into there, that voltage didn't really kill me, but it definitely hurt. Anyway, what is voltage? Instead of measuring electric potential energy, we measure the potential difference, and that's called the voltage, right? The potential difference is called the voltage. So when we say potential difference, the potential difference is that, right? This distance right here, the difference right there, okay? So voltage, the amount of work it would take to move a charge between 2 points divided by the value of the charge, okay? So voltage equals work divided by charge, right? Voltage equals work divided by charge, or V equals WQ, right? Of course, voltage is the big V. That's the unit, right? And then it equals 1 joule per coulomb. Voltage equals 1 joule per coulomb. When we have electric potential energy, this may be used to set up an electric current, right? Which you've seen it before because when we did our lab, right, on Friday or Wednesday or Monday, both days, right, on a battery, right, one side is positive, right, and the other side's negative, right, and then it had to travel from one side to the other, and that made work. That did work, right, through a wire. That was a complete circuit. So that's what this means. That's what this means. So that's voltage. Let's talk about ohms now. So there's this thing called Ohm's law. Another guy named George Ohm. I wonder if there should be an E there, because otherwise it's like Horge Ohm, whatever. Ohm's law, right? Wherever there's an electric current, there is resistance within the conducting material. R is due to atomic and subatomic collisions, right? The resistance, okay? So George Ohm formulated this relationship between the voltage, the current, the resistance, where the voltage equals the current times the resistance, right? And so when you were doing the lab on Monday and Wednesday, you notice that the more batteries you put onto the series of circuit, the brighter it got, right? And that's because you increased the voltage and you infused the current. But then some of you put extra light bulbs in there, right? And what happened to the light? It got dimmer. And that's because the resistance increased, right? That's because of the resistance increased. Okay? And generally, right, adding a light bulb on its own doesn't actually make resistance increase, but it's actually the filament that's inside the light bulb that makes it decrease, right? Who invented the light bulb? Thomas Edison, I believe. So Thomas Edison tried like 500, 1,000, I don't know, all kinds of different material, right, to get the right filament to put into a light bulb, right, that would light up, right, and make it bright without burning it down or exploding or not doing anything at all. And I can't remember what the old filaments used to be made of, what he figured out used to be made of, right? But that filament is actually what causes the light. The filament is what causes the light. But that filament is also what introduces the resistance into the circuit, right? These days, we don't use those kind of light bulbs anymore, right? These bulbs here are, anybody know what these these fluorescent bulbs run on? It's not a filament. Anybody know? It is a gas. What kind of gas? It's mercury gas, right? It's mercury gas, which is actually very interesting because has anyone ever watched that movie 40-Year-Old Virgin? And remember that one part of the movie where Paul Rudd and all of them were like hitting each other with like, I'm like, that's not 40-Year-Old Virgin, was it? What movie was that? There's a movie where Paul Rudd was was hitting. They were working in an electronics store, and they had like light fluorescent bulbs, and they were like breaking them on each other's legs. It might have been 4-year-old version, right? That's super dangerous. Don't do that. Mercury can kill you. so, so yes, mercury. Not to say nothing of the fact that the glass would put shards of glass in your leg, right? So Ohm's law is again voltage equals uh what's I again? Current. Voltage equals current times resistance. Okay. 1 ohm is equal to 1 volt divided by 1 ampere. Okay. So here's your question, right? Which is not true about Ohm's law? Ohm's law measures voltage. It originated with George Ohm. Ohm's law can equal this, can be V equals IR, or 1 ohm equals 1 volt, 1 ampere. This one might be a little tricky, but if you've been paying attention, you'll get it right. While you're doing that, so if you've ever wondered why using fluorescent bulbs is cheaper than using regular light bulbs, it's because flowing electricity through the mercury vapor, right, has less resistance than flowing it through a filament. So the electricity doesn't have to work as hard, right, to make it bright. And that's why people go through and change all their light bulbs out with fluorescent bulbs. And now everybody's moving to LED, which apparently can last like 20 years on one bulb, right? And much cheaper, right? I think they say like 4.6 watt LED light bulb is equivalent to the 100 watts light bulb, right? Right? But that doesn't translate to the heat that's given off by a naked body, though, right? That's not the same. You still need to have the naked body thing with 100 watts to keep warm. It's getting cold out there. I'm just saying. It's getting cold, right? And if your body's giving off 100 watts of electricity, not electricity, of heat, right? As the same amount of heat as a 100-watt light bulb, incandescent light bulb, not LED light bulb, then that's the way to stay warm. Get naked and start hugging on each other. It's good. It's a good time, I promise. It's a good time. It's a good time. All right. Oh man, everybody's already answered. Sorry, getting distracted by naked people. All right. Okay, so the vast majority of you got that one right again. Ohm's law does not measure voltage, even though you can rearrange it to see a voltage there. Ohm's law is meant to measure what? Resistance, right? Meant to measure resistance. Good stuff. Measure resistance. All right, so let's talk about a simple electrical circuit, right? A simple electrical circuit. Just like we saw in our lab, right? Electrons flow from a negative terminal to a positive terminal, right? Provided that the chemical energy of the battery is sufficient, right? So electricity flows from negative to positive, which makes sense because electricity by definition is the flow of electrons, right? And so it can't come from the positive because there's no negative, there's no electrons on the positive side. It's all on the negative side because electrons are what? Negative, right? So an open switch, right? That's a not complete circuit with no flow of electrons, no current, right? So this is synonymous right here. These two can mean the same exact things. Current is the flow of electrons, right? The flow of current is also the flow of electrons. And so if you have your switch open, right, swung to the other side, as they said in the instructions, which I had no idea what that meant either, right? But swung to the other side open, right, then the switch is open. If the switch is closed, you can complete the circuit, and now there's a flow of electrons that exists, right? Closed circuit is required to have a sustained electrical current, right? Sustained electrical current. Sustained electrical current. So let's take a look, take a gander, as it were, at a simple electrical current. And this is what you did in lab last week, right? This is what you did in lab last week. We have here a battery. Looks like a 9 volt, right? Except that we use D's. Didn't we use D's? I'm pretty sure we use D batteries in the lab, right? And so here's the light bulb, right? This is definitely a incandescent light bulb, so it's emitting that 100 watts, right, of heat that bodies need to survive when they're pressed up against each other naked, right? And so electrons here flow in this direction towards the light bulb, lighting up the filament inside, right? Because it's heating up. That's why it's so hot, right? And then go over here back to the positive side. Good stuff. Good stuff, right? So here's the circuit diagram, which somebody was trying to draw a circuit diagram in lab last week, and I'm like, no, don't do that. I don't know what I don't know what those symbols mean. Just draw boxes and label them, please, right? So apparently this here, right here, one line that's short and small means battery, right? And then two dots together is a switch. An arrow is showing the flow, right? And then this here is the resistance, which is, see, I'm right. The filament is causes the resistance. Man, I was guessing on that. I guess I was right. That was a lucky guess, right? So resistance here, and that means the light bulb right there. I don't know if you all knew this, but I literally have no idea what these things say beforehand. I just see what's on the slide and I just tell you about it. So I'm just winging it, just like you guys are. I'm winging it. Life is about winging it. Okay. So here we have the water wheel analogy. So here we have again, we have our closed circuit with our light bulb, right? And it actually can be analogized to a water wheel, okay? So we have a pump here, right? And the pump can be the battery. And it's pumping water in a certain direction, right? We've got the valve here. The valve here can be the on switch, even though there's not an on switch there, right? But if you had a switch right there for on and off, that could be the valve, right? And then the flow of electricity here, right, is the same as the flow of water. And then that flow of water here turns this wheel, right? It turns this wheel. And that turning that wheel is doing work, right? And the light bulb is like that. You're doing work here when you light up a light bulb, right? And you're also doing work here when you're turning this wheel. Maybe you're like milling grain or something. I don't know who uses this thing anymore, but yeah, maybe you're milling grain or something for grain alcohol. All right, so your next question is this. In the water wheel analogy, the pump represents what part of the electrical circuit? The pump represents what part of the electrical circuit? Speaking of electrical energy, I'm starting to run out of gas here. All right. 21 people have responded. We have people answering all the answers, but that's okay because the vast majority of you answered B, which is correct. The battery is the water wheel. I mean, not the water wheel. The battery is the pump. The battery is the pump in this analogy right here, right? The battery is the pump, which is interesting because the pump's got to be doing some work too, right? Like where did the work come to make the pump go around, right? So there's got to be like another battery or something or a person turning it, right? Turning that pump. Here, chemistry is doing the making all the electricity, right? But what's making that happen? Kind of an incomplete analogy if I say so myself. But what can we do? So here's some things about electrical power, right? Some things to remember about electrical power. Recall that power equals the work divided by the time, right? That was from chapter 4. Also remember that voltage equals the work divided by the charge. That was from chapter 8. You can rearrange these things now to say to say work equals the charge times the voltage, right? The charge times the voltage. Then you can substitute some stuff, and now the power equals the work divided by time, right? So I'll do all that math, rearranging, right, which I'm not going to make you do, but what you get is that power equals the charge times the voltage divided by time, okay? I promise we're getting somewhere with this. I'm sure we're getting somewhere with this. I think we're getting somewhere with this. So also to recall that the current equals the charge divided by the time. So therefore, right, therefore, the power equals what? The current times the voltage. Oh, that's where we're getting to. That's what we're trying to do. Yes. So all this here is just to say that power equals the current times the voltage, right? Also, power could also equal uh, uh, what is that called again? Oh, sorry, current squared times the resistance. So P in watts, I is in amperes, R resistance is in ohms, and V is in volts. Okay. So how do we use all that? The two important things here are this equation and that equation. You don't have to worry about how do we get there, but those two things. Again, I'm not going to make you do anything with math, but I might ask you, if I increase one side, what's going to happen to the other side, right? So let's take a look here. We find that we find the current and resistance of a 60 watt, 120 volt light bulb in wow, we use a lot of light bulbs here, right? 60 watt, 120 volt light bulb. So I guess that means it's a lamp that you plug into the wall that's 120 volts and it emits 60 watts, right? So we know that we know that power equals current times voltage. So we can rearrange it around, right? Where now current now equals power divided by voltage. So that's going to be the 60 watts, right? Divided by the 120 watts. And then we get 0.5 amps, right? That's how we get we find the current, okay? We can't go straight to finding resistance yet because we got to figure out what the I misspoke. Sorry. We're looking for resistance now, right? So we can use the voltage equals the current times the resistance, rearrange that around, right? And we can then use the 120 volts and then use the amperage that we just found, the 0.5, and we get 140 watts, right? And then from that, we can take that 120, 40, we have the 240 watts, okay? So now we have the power, and that equals the current squared times the resistance. Now we can solve for the resistance again with the 60 watt light bulb and the 0.5 amps squared, and now we know that the resistance of that light bulb is 240 ohms, right? 240 ohms. Which is crazy because that light bulb there has a lot of resistance. That's why your electricity bill is so high when you use incandescent light bulbs, right? So stay away from those incandescent light bulbs. They may keep you warm, but they cost a lot, right? They cost a lot of energy. Oh, by the way, I forgot to say this too. Uh, for ohms, right? The unit for ohms is omega, the Greek letter omega, right? Which, if you didn't know, omega is the last letter of the Greek alphabet, right? So omega stands for ohms. You can remember it too because it kind of looks like an O for omega and O for ohms, right? All right, let's do something else here. We have a coffee maker, okay? And it draws 10 amps of current operating at 120 volts. Have you ever had this problem where in your kitchen you've had so many appliances plugged onto one plug that it just blows the breaker, right? People are shaking their heads like this has never happened to them before. It happens to me all the time, right? So, like for example, you'll have a Keurig, a refrigerator, and a stand mixer, and a toaster oven, and a microwave all in one circuit, right? And then it blows your breaker. Well, the reason why it does that is because most of the circuits in your house are rated for a certain number of amps, right? And if you exceed those amps, that's when you blow the circuit, the breaker, and you have to go and reset it from the garage or wherever your breaker box is, right? So there are circuits in your house that have higher amperage, like higher rated amperage than others. So things that require that you have the higher amperage are things where your washer and dryer are, right? Have you ever noticed that when you put in your washer and dryer, uh, uh, I don't know if any of you ever bought a washer and dryer or moved into a house and had to install a washer and dryer, but both washers and dryers, they take up a lot of amperage. So they actually run on 240 volts, not 120 volts like most things do, right? And that's the reason why, because it takes so much voltage, because it takes so much amps to run those things, right? So, um, uh, but even on the 120 volt ones, right? If you get enough things on that one bulb, not one bulb, that one circuit, right? You on the 120 volt, you can blow that, and you have to go reset your breakers in the breaker box. It's a great time doing that kind of thing. So this coffee maker, this Keurig right here, right, runs at 10 amps, and it's currently operating 120 volts, and that's just a normal American household, right? Normal American house at 120 volts. That's not in the garage or not in the laundry room where it's 240, right? If you have a hot water heater that also runs on 240, because it turns out it takes a lot of energy to heat up hot water. You remember that from the last year we had, how heating up a little bathtub of water costs 8.28 cents, right? Um, so given that you have the amperage is 10 and you have the voltage is 120, right? How much electrical energy does this coffer use each second, right? Holy crap! Each second, this thing uses 120 watts. I mean, 120. That's good. Uses 1,200 watts. That's crazy. I'm turning off my Keurig because this thing is really expensive to use, right? Every time you brew a cup of coffee on your Keurig, it's using up 1,200 watts of electricity, right? And hell, most people on TXU, like when they your plan, right, is usually staggered, where you start out like 11 cents per kilowatt hour, but then you go past like 1,200 and it's like 13 cents per kilowatt hour, and then you go past like 2,000, it goes like 15 cents per kilowatt hour. So like that's not good. You've already used up so much of your allotment there. All right, so just a quick review of the equations here, right? We have our current equation, which is I equals QT, right? Like I equals quick trip, right? Where actually I equals quick divided by trip is what I meant to say there. And then we have Coulomb's law, which is a lot like um, Newton's law of gravitation, right? What is the most important thing I want you to know about Coulomb's law and the Newton's law of gravitation? It depends on the distance, right? It depends on the distance. The bigger the distance, the less the force, right? Remember that for both Coulomb's law and for Newton's gravitational law. And then voltage equals work divided by charge. That's in joules. Ohm's law is V equals IR, right? Which is funny because V is voltage, but we're talking about we're talking about R there, so that's why people get confused. And then electrical power. The electrical power can equal IV, right? Current times voltage, or I squared, current squared times resistance. Okay. All right. Here's a tricky one. Here's the next question. A little tricky. What formula is for current? What formula is for current? It's not that tricky. I'm just kidding. I'm totally kidding. It's not that difficult. Let's see how everybody did. Oops, I don't want to go settings. This will be the last thing we do today, so let's see how everybody did. And then we can go over to the lab. Formula for current. Only got 17 people. 22 now. Oh my gosh. How did you guys do this? Oh, the vast majority got it right, right? What is I? I is current, right? So the answer is A. Okay. All right, that ends today's lecture.